So we've been doing the review session. So maybe you can try this one for me real quick. So we have lithium, calcium, the fluorine, argon. And I just want you to find which one is your alkali metal, okay? Or alkaline earth metal, okay? Or which one is halogen, and which one is noble gas. That's it. Okay? So look at those elements and see which one is which. So based on this type of question, you just need to look at the periodic table. That's it. Okay. So for example, lithium is a group 1. So group 1 element is alkali metal, except hydrogen. So hydrogen is not metal, but except the hydrogen, they're all alkali metal. If you look at the calcium, this is in group 2. So if it's group 2, it's alkaline earth metal. Okay? So it's not so reactive as the first one for group 1 element, but somewhat. And then if you look at the second last column in periodic table, this is group 7. This is what we call halogens. Halogen. H-A-L-O-G-E-N. Halogen or halogen. And that is group 7. So second last column is the halogen. Okay? And the last column in your periodic table is, as you know, noble gas. Okay? So whenever you have this type of question, you just need to look at the periodic table and just find them where they are. All right, so maybe you can try this one real quick. Try it and try to look at the periodic table right there. Okay, so the helium is what? Noble gas, right? This is in the last column. If you look at the chlorine, is in second last column, so it'll be group 7. So that is a halogen. Okay. So if you look at the magnesium, it's in group 2, second column, so it'll be alkaline earth metal. Alkaline earth metal. And then potassium is in group 1, so it'll be alkali metal. There. It's pretty. Just look at the periodic table and try to find them on the where they are. Okay. All right. So maybe you can try to name those 3 compounds. Okay. Okay. So try to name those 3 compounds by looking at the chemical formula. It looks better. Okay, about 1 or 2 minutes. We'll do this together. Okay, so the first one, if you look at this first element here is a transition metal. So that is in the D block. So this is the cation, which is a metal, so metal cation. And this is a non-metal, because it's on the right side of the periodic table. So this is the non-metal. elements. So if they bond together, they form the ionic bond. So it would be ionic compound. So for ionic compounds, it's pretty simple. You need to copy the first element, name, ion. Okay? And then you just need to use the core name of the chlorine, chloral, and put ID. So that is the basic form of the ionic compounds. But just one more thing for ion, because ion is in group the block A, okay, D block. So this is the transition metal. If it's in the D block in the periodic table in the center, I mean it's a transition metal. So when it's transition metal, you just need to put the charge number in Roman number in parentheses. Okay? So that will be not just iron chloride, will be only partially right. You need to more specifically iron 3 chloride, because when you look at the the chemical formula, the chlorine there, 3 chlorines bond to iron. But each chlorine is -1 in ion form, but there's a 3. So what it actually looks like is this one. That is what they're doing right now. Okay? So that will actually tell you the ion has a 3+ charge, because there's a 3 chlorine with a 1 negative charge. So that makes a 1 neutral ionic compound. That is why you need to put the numbers in parentheses to be 100% clear. You have if you have any other metal, like in a group 1 or 2, like sodium chloride, you don't have to do the number, because you know sodium is always +1. But if you have metals in the D block, you have a different charge for sometimes. So maybe it could be iron 3 chloride, but sometimes it could be iron 2 chloride, that would be CO2. So to distinguish these two, we put those numbers in parentheses, that's one. Okay. All right. So this one, so nitrogen is non-metal. Okay, nitrogen is not metal. It's on the right side of the periodic table. Oxygen is also non-metal. So it's non-metal to non-metal. So non-metal to non-metal, they make the molecular bond. Okay, so when they make molecular compound, you just need to number each. So it'll be 2 nitrogen and 5 oxygen. So it'll be 2 means nitrogen, and 5 means pent. So pentoxide. So this is the same as ID at the end. OX coming from oxygen, and the pent means that there's 5. So there will be 2 nitrogen, 5 oxygen with IDE. So we call this dinitrogen pentoxide. So if you try this one instead, what would that be? Perfect. Trinitrogen pentoxide. Perfect. That's it. Okay. So that's what you can do whenever you see your first element is not metal. Okay, means it has to be molecular bond. Okay, so this is molecular compounds. It's ionic compound. This is the acid compound, meaning they're going to donate the protons. Whenever you have this type of compounds, what you need to think of is look at your anion part over here, okay? Which is phosphate with a 3 negative charge. So whenever you have ATE names with phosphate, you can change it to the IC acid form when you put the hydrogen on it, 3 hydrogen. Because it's 3+ charge, that's why we put 3 hydrogen on it. Because so each hydrogen in ion form will carry 1+ charge. So this is the phosphate, but when you put in the hydrogen, it becomes acid. So in that case, you just need to put IC acid, so it'll be phosphoric acid. That's the name of it. Okay? So because you started from the phosphate, which is this one, and whenever you have a phosphate-based acid form, just change it to the IC acid. So it'll be not phosphate, but phosphoric acid. You guys actually remember this one? It's a long trip, right? So if you change it to 3, that's actually phosphite, is ITE. Whenever you have an ITE, you change it to OUS acid. So in this case, you just need to do not IC acid, but OUS. So it's phosphorus acid. Okay, we have one less oxygen than you have the AT compounds. It just be ITE, so the phosphide. Okay. So this will be phosphide. Okay. And then from here, acid form will be phosphorus acid. Okay. So if you get one less, even further, you just need to put hypophosphorus acid here. Okay. If you get maybe even higher than what you have, like maybe it was 4, or change it to 5. So it's actually one greater number of oxygen than 18A. And then you just need to do, so initially you put IC acid, right? Phosphoric acid. In this case, you get one more. So it means now we're gonna put per. Means it's more than what you have for 18. So we per phosphoric acid. So let me give you one more example real quick and move on. Okay, so maybe, okay, so this is the sulfate. This is the sulfate, ATE. Sulfate. Okay, and then you have maybe H2SO4, and you just need to change it to IC acid, right? So it's going to be sulfuric acid. Okay. But if we just change it to the one higher, will be per sulfuric acid. Okay. If it's the one lower, will be sulfurous acid here. Even lower than that will be hyposulfurous acid. It's the same. So only thing you really have to know is when you look at the acid compounds, one might be the anion form, which is an AT name or IT name. When it's with the hydrogen, you can do it. You can convert it to IC. Yeah, go ahead.
So what was the answer to
Which one? The A.
the
This one? This one?
no, the last one you just did.
The last one? Oh.
Yeah.
Last one. Okay. This one will be hyposulfurous acid. Okay. Hyposulfurous acid. Makes sense, right? Okay. You can also look it up on the campus. Okay. All right. So let's move on. So let's try. So yeah, I've been doing the review session. So please watch those on the YouTube too if you haven't watched it yet. So okay, so here's. Okay, so I might ask you for the definition of these two. So one might be the oxidation, one might be the reduction. Okay, so oxidation simply means it's the loss of electrons. Okay, loss of electrons. So that's okay, and the reduction means it's a gain of electrons. This is I want you to remember. Okay. So, for example, if you have hydrogen gas coming into the maybe ion form, this will be what? Oxidation, because now it has what? Lost to 2 electrons as becoming kettling. So there'll be 2 plus charge in there. So oxidation number become positive. So that means they lost the negative number, which is like electrons, so the oxidation. But most importantly, just remember these 2 definitions. So oxidation is a loss of electrons. The reduction is a gain of electrons. There should be just, yeah, 0.1. This is a very good one. So when you have a system here, and you have a surrounding on the outside. So except the system, everything else in the universe is surrounding. Okay, surroundings system over here. So when heat energy is going out from the system, we call this what reaction? Do you guys remember this? If a heat is going out from the system, perfect. Exothermic reaction. And this will be showing you some negative sign on your enthalpy change. Okay? Negative sign for the enthalpy change for the reaction. And then when it's going in, it will be endothermic reaction. So then enthalpy change of the reaction will be positive number, some positive number. So this should be negative sign. Okay. Do you guys remember this actually? Alright, so there's just one more thing I want you to know is delta Z. Okay, so it's a Gibbs free energy. It's a Gibbs free energy. So only thing you have to know about this one is when your Gibbs free energy change is a negative, means it's a spontaneous reaction. Spontaneous. So spontaneous reaction simply means that the reaction will happen almost automatically without, you don't have to do anything. When you put them together, they'll just do the reaction almost right away. Because they will be spontaneous reaction when they show the negative number for Gibbs free energy change. So they can do the negative change, so they'll be more stabilized at the end. So they do that because they want to more stabilize. So everything in the universe always tend to go into the more lower energy state. That's why when it's negative, it'll be spontaneous because they want to stable even more and more always. Okay? So that means if it's positive, they will have non-spontaneous reaction because whenever they do the reaction, they'll be even more unstable. So they don't want to do the reaction unless they are forced to. So when you want to force them to do the reaction, when the Gibbs energy change is positive, you have to give them a lot of energy. So when they give a lot of energy, then they can do it. But unless you put a lot of energy into the reaction, it will not happen at all because it's a non-spontaneous reaction. Okay, makes sense, right? Yeah. Just remember this. Okay, so maybe you can try this one. Quick. This is the Hesse's law. Then final equation is this one. And you just need to know the one after the enthalpy change for the final equation using these two. Okay, I'll give you 3 minutes because you have to do a bit of a. Oh, the second one was 788. Okay, I'm not gonna lie. Exactly the same question you'll see on the finals. Okay, about 1 minute. So yeah, let's do this together. So once again, every time you see this type of problem, you always start from the final one and just look at where those reactants and products are. So you have the carbons and the oxygen molecule on the left, which there looks just fine because this is where they're already on the left side. But the problem is you have carbon dioxide on the right on the final equation, but it's on the left on the second. So that means you have to flip this one. Okay, so I'm gonna flip this one now. So that if you flip this one, it will be 2 carbon monoxide plus O2 will make 2 carbon dioxide. So whenever you flip this one, you just need to do the same thing for your enthalpy change, which is multiplied by -1. Because now you're going into opposite direction. So that's why you have a different sign for that enthalpy change. Because you actually the other one. So if you do that, okay, you can just add them all. Okay, so you have these ones are canceled because you have the same thing on the left and the right. Okay, so they can be canceled, and just copy the rest. And there'll be 1 O2, another 1 2, so it'll be 2 O2. That makes the 2 carbon dioxide. Okay. So if that is the case, we're almost done. Okay, but this, if you look at these two, it's half of what you have over here. Because it's 2, 2, 2. It's a 1, 1, 1. Okay, so this is another rule we have for Hess's law. So whenever you have the enthalpy change, also you can half of the enthalpy change will be the same as this one. So when you combine these two, will be -222 plus -788, not plus, because we flipped it, so it'll be negative, right? So it'll be in total -1010 kilojoules. It's a -222, it's a -788. So if you add them all, it will be -1010. Okay, and this one was for this one. Okay, and then if you just divide both sides by 2, 2, 2, 2, it will be 1, 1, 1. So that's what you're wanting to have for the enthalpy change. So you do the same thing on that enthalpy change. So just divide this -1010 by 2. Okay, and then you finally have your enthalpy change for the final equation will be just -505 kilojoules. Okay, so yeah, you'll see the same question on. So you just need to know how to do the calculation. All right, so copy them all right. Okay, so then let's move on. Okay, so if you have the light is at 400 nanometer wavelength, okay? And then what might be the frequency? What is the frequency of the light? What might be the frequency of the light? And then the speed of light, C, is 3.0 times 10 to 8 meter per second. Okay, so you have a light is at the wavelength 400 nanometer. Okay, and what might be the frequency of that one? And the 1 nanometer is equal to 10 to 9 meter. 10 to 9 meter. Do you know how small 1 nanometer is? If you make the 1/10 of the 1 nanometer, that is the size of most of the atom. This is really small. Okay, but 1 minute. Okay. Yeah, let's do. Okay. Okay. So what I'm gonna do first is I'm gonna convert this numbers in meter, because whenever you put this in the equation, your speed of light is in meter per second. The equation I'm gonna use is speed of light always equal to wavelength times frequency. Okay. So. But to get to this equation, you need to have a unit conversion for this wavelength, because it's nanometer, not meter. But your speed of light is meter per second. Okay? That means your frequency should be in per second unit, meaning how frequently something will happen per 1 second. That's frequency, literally the frequency. Okay? So whenever I do this one here, so just copy this number, which is the speed of light, 3.0 times 10 to 8 meter per second. And then wavelength, if you do the unit conversion, 400 nanometer, okay? And you have a nanometer over here, okay? This is 1 nanometer, and you just need to do 1 times 10 to the 9th meter. So nanometer will be canceled. So if you do this, you'll find the numbers of 4.0 times 10 to negative 7th meter. Okay? So 400 nanometer is equal to 4 times 10 to negative 7th meter, okay? When you do the unit conversion over here, okay? So if you do that, and times x. So this is what we're solving for. So to get the frequency, you just need to put your wavelength in meter now. It's a unit converted already, and put on the other side. So once this is multiplied, but when you put it on the other side, it will be divide, right? So it will be 4 times 10 to negative 7th meter. Okay, so as you can see, the meter will be canceled, top and bottom. That's how I can get the numbers for per second, which is the frequency here. Okay, so whenever you do this one, 3/4 is what? 1.75. Okay, and then 10 to 8 divided by 10 to negative 7 is the same as 10 to 8. Because this is dividing, right? So it'll be minus. And then this negative 7, so it'll be u minus negative 7. So it's actually the same as plus 7. So it will become 15. Okay? So this is the same as, when you do this, this is 0.75 times 10 to 15th per second. Okay? But when you want to put this in the scientific notation, you need to have that first non-digit number before the decimal point. So I'm going to move the decimal point to the right once. Okay, so if you do that, actually it's a 7.5 times 10 to 14th per second. Because when you move this to the right, you just need to put minus 1. Okay, so it'll be 14th. So the answer is 7.5 times 10 to 14th per second. Can I move on? Okay. Alright, so can you guys do, whenever you have a light, it's at 600 nanometer, okay, 600 nanometer, what might be the energy of 1 photon? And the Planck constant is 6.626 10 to negative 24 joule times second. Planck constant is 6.626 times 10 to negative 34 joule times second. So joule means the unit of energy. It's amount of energy you can accelerate the 1 kilogram matter in 1 meter per second faster. Okay, about 1 minute and we'll do this together. Okay, about 30 seconds. Okay, so okay, here's the thing. This is just a quick reminder, okay, right? So 1 photon energy should be equal to Planck constant times frequency. Planck times frequency. But the problem is we only know the number for wavelengths, not the frequency yet. So what you need to do is what we just did before. Okay, so we have lambda times frequency is equal to speed of light, right? So we can actually put this one as the same as, so if we put the lambda on the other side, the speed of light over wavelength is equal to frequency. So instead of the frequency, we can do speed of light over wavelength. That's the same thing actually. So we can do it this way. So if you write this one here, Planck constant is what? 6.626 times 10 to negative 34 joule times second. Okay. And the speed of light is what? 3.0 times 10 to 8 meter per second. And then the wavelength was 600 nanometer. Okay, so we'll do the unit conversion for this one to meter again. That will be 6.0 times 10 to negative 7 meter. So if you do the unit conversion like you did for previous one, 600 nanometer should be equal to 6.0 times 10 to negative 7 meter. Okay, so same thing here. When you do this one here, think about it. The 3 over 6 is same as a half. 0.5, right? So this 0.5 times what? This is the same. 10 minus negative 7 is what? 10 to 15 per second. So we have a frequency here, but we want that, you know, on the other side, right? So we want to put the decimal point right after the first non-zero limit, which is 5. So it'll be 5.0 times 10 to 14 per second. So these two numbers are the same. We just put it in the scientific notation. Okay? So does it make sense, right? We could. Okay. So this is the same as 5.0 times 10 to 14 per second. Okay. And if you look at this one, if you multiply the one with the joule times second, the numbers in per second, so this will be canceled. Okay. So that's how you can get the numbers in joule. That is literally energy in 1 photon. Okay? So when you do this one, this will be the 6 times the 5 will be I think 33.13. 10 to the, so this is a negative 34. This is multiply, right? So plus 14, not minus, because it's not division here. It's multiply. So that will be negative 20th joule. Okay. And then you just need to do what? Scientific notation, because you want to put decimal point right after first non-zero number. So I'm going to move it actually to the left. That means you have to do not minus, plus 1. So this will be 3.313 times 10 to negative 19 joule. So that's the answer. Make sense, right? All right, let's do a bit more mathematical problems today. So once again, if you know just how to do this one, it'll be much easier for binary. So if you have one electron, falling from N2, energy level 2, to ground state, which is N1. One might be the emitted light or energy from this one electron. Okay, that's the question. So you have one electron falling from the higher energy level to the lower energy level. When they do it, they release the energy, certain amount of energy. So one might be the energy for one electron coming from the N2 energy level to ground state energy level 1. Okay. Okay, so here's the thing. So whenever you have an energy change, we have the Rydberg equation, which is a negative 2.18 times 10 to negative 18th joule times your n or n squared over 1 over n squared, the other n squared, and this is the final state. Okay, this is final state. This is your initial state. So this is a negative because it's an emitted energy, meaning this actually losing the energy. So that's why we put the negative sign. Okay, so, but this is just literally means how much energy will be released from this electron. So whenever you have this one over here, you just switch the n final initial onto here. So final state is 1. So I'm gonna switch this one to the 1 square, which is still 1 anyway, okay? And then this is the initial state, which was N2. So this will be 2 squared, which will be same as 4, right? Because 2 squared is 4. So what I'm gonna do is 1 minus 1 over 4, okay? So that will make you, what? 3/4, right? 3 over 4, okay? So when you multiply this number by 3 over 4, that's the answer, okay? So that would be negative 1.635 10 to negative 18th joule. Okay? So either you can say negative 1.635 times 10 to negative 18th joule, or you can say this amount of energy is just released. So released already has a negative meaning there already. So either way, but maybe you can just, in a number, you can just put negative. All right, so okay, just all right, this will be the last one today. Can you guys put the electron configuration form of potassium cation, longer version and shorter version together? So it's not just potassium, it's a potassium cation. Okay, so one might put the electron configuration form of potassium cation in either longer version or condensed version. 2 ways. So, like I said before, whenever you the electron content, you need to look at the periodic table right away. So you just start from the left top corner to the right, and top from the bottom, and see which column is S, which column is P or D blocks on this one. Okay, there's a hydrogen, helium, lithium, and so this is B block. Okay, so this is the what? S block. First period is S block always, and first and second column is also S block, except the first period, the last 6 column is P block, and somewhere in the middle is D block. and some column down into D is F4, which we don't normally care. Okay, so if we just here, K is right here, right? So I'm gonna do 1S, 1, 2, 2S, 1, 2, 2P, because P block, 2P, 1, 2, 3, 4, 5, 6, okay? And 3, right? 3S2, 1, 2, 3P6, 1, 2, 3, 4, 5, 6. And now you get 4S1, okay? But which you have a plus 1, so that means it has lost 1 electron. So that will be same as electric configuration form of argon. So if you want to do condensed form, you can put the argon in the bracket. If you want to do the longer form, you just need to do this one, okay? Just following the periodic table, where there's a P or S or D or F block are, and you just come from left to the right, top to bottom, that's it. All right, so I will stop here today. Let's do